Hi, in this video you learn how to derive the centripetal acceleration formula. First of all, let's take a look at the equation that we need to derive first. So in your data booklet, actually you can find it in topic 6. And so let's just copy here. We have A equals to V squared over R, or we can have 4 pi square R over T squared. So you can find the two different forms of representing centripetal acceleration formula here. In fact, there are actually more than two. There are actually 4 altogether. If you try to look at the data booklet very carefully, down below here, this is actually the F equals to ma. Can you see that? The A is actually V squared over R right here. Alright, I mean, if you look at this whole thing, this is F equals to ma, and the V squared over R is actually the A. Here, of course, we refer to centripetal acceleration. Then that is obviously included above in the second row. But then if you look at the third row here, then you can see A, you can somehow see quickly that A equals to omega square R as well. So this is actually the third form. For omega, actually I should write it as this, right? There's a little circle here, times R. So this is a third form of the centripetal acceleration formula. So you may be wondering, where is the fourth form then? If you look at your textbook, then you can find V squared over R, that's what we got. Omega squared R, that's what we got for the third one. This whole thing is the second one that we got. And lastly, there's one more. Let's just copy it from the textbook first. So 4 pi square R F squared. So from now on, in our video, I assume again you also put this in your question set as well. Let's just call this equation 1, 2, 3, and 4. The reason why I name it with different numbers is later on we can refer to the equation very easily, and then it's similar to the kinematics equation where we try to solve certain examples. Then we may choose one of these equations depending on which one is more convenient, and then we'll be using it. Right, but that's something we'll do in the future, in maybe the next video. Okay, and for now, the most important thing is, do we have to prove all this equation or not? And the answer is no, not really. What you have to do is, I would say you have to prove the first one only. So V squared over R is kind of like the mother of the other three. So if you have this one, then you'll be able to find the others. So please trust me on this first. Let's just try to derive the first equation, and then we'll be able to do the other three very easily once this is done. Before I set you free to explore the joy of deriving this equation yourself, let me tell you some basic definition first. So I think the best place to put it would be in the space on page 2 here. The definition that you may care about will be V and omega. Remember, they are definition. Okay, you cannot argue with definition. It is what it is. So for the first one, V, it is linear velocity. So like what you see in the previous video, we are talking about the velocity vector. Oops, not a very good circle. The velocity vector, let's say this is an object and moving in this direction. This is the velocity vector. It's always tangential to the circle, and it is the direction of that object moving at that moment. Of course, together with the magnitude of its speed as well. And so if you define a circle with the radius r, then what could it be for linear velocity? Think about this. For the whole circle is perimeter. That means the circumference will be 2 pi r. Right, the whole circle is 2 pi r. So that is to say, together with period to be t, that means period means the time that it takes for completing the whole circle. Then how do we relate this? It is as simple as 2 pi r over time, distance over time equals to velocity. So this is an equation that you need. Alright, if you want to rearrange it, it's up to you. Okay, this is one of the definitions you may have. For omega, that is obviously another velocity, and we call it angular velocity. Angular means something to do with angle, obviously. The reason why we will need to have angular velocity is that when you are moving in a circle, we may not care about its linear velocity because the circle may be bigger or smaller. We may just care about how fast it completes a circle. So when we talk about angular velocity, that is talking about how much angle you pass through in 1 second. So in terms of unit, earlier for linear velocity, the unit would simply be meter per second, like how you have been learning for many years. For angular velocity, this is in a unit of radian per second. Radian is a unit of angle. And so obviously for its definition, it's not about the circumference. Okay, it's more about the angle. So we will use 2 pi. So in case you have never learned about radian, then 2 pi is a radian unit, you may call, to describe the angle, and that would equal to 360 degrees. So for completing the whole circle, you need t, again, period t, that much of time. And by calculating this, you'll be able to find the angular velocity, which is radian per second. So this is how you can get the unit, radian per second. Okay, so with these 2 definitions, I think you are good to go. You may now want to pause the video and try to prove again the first equation, A equals to V squared over R.
2,000 years later.
Alright, so let me show you how I would do it. If you try to Google it, you should be able to find 4 at least different approaches to do it, or even more. So I'll show you the simplest one first. So for this one, I have already drawn a circle with a radius r, and so imagine there's an object moving in this circle with velocity v1. Let me just draw it a bit more like 90 degrees. Alright, I'll try my best, and also longer for just easier to see. And so a very short instant after, okay, here, then that will be again another direction, and that will be v2, right, after a certain bit of time. And of course, due to the acceleration, the direction of the velocity will get changed. And since this is tangent, and this is still 90 degrees. And now let's just define this angle to be theta. And if we want to prove the equation that we are looking for, then obviously one thing that you should recall is the fundamental definition as well. And let's recall acceleration will be dv over dt, or if you don't want to express it with calculus, then at least delta v over delta t. In fact, what you are doing with dv over dt is like taking the limit of delta v over delta t while delta t tends to 0, right? And so I mean, this is a more fancy way in IB physics that if you want to express it. So let me just stick with a more simple way. So delta v over delta t first. Alright, so now the question would be, how do we express delta v and delta t from our diagram or from our situation? So let's think about delta v. Delta v is simply v2 minus v1. And so probably we want to move the vector a bit so that we can find the head-to-tail method. So we can actually move it like this. Alright, this is v1, this is still 90 degrees, and this is a legit move because we didn't change the direction at all. So if this is theta with this angle, then obviously this one is 90 degrees, and so this one is 90 degrees minus theta for this angle. And so for this angle, because this blue line is a straight line basically, and then you have 90 degrees here and 90 minus theta, and so this one will actually be theta. Okay, and if you try to shuffle the v1 around towards this, then you should be able to find a triangle like this, v1 v2 with the angle theta. So that means this angle between v1 and v2 is the same as the angle of from the center of the circle. So then now the question becomes easier because you want to find v2 minus v1, right, for delta v. And so v1 negative would then be the opposite right, as we learned in chapter 1. So the delta V would then be head-to-tail method, then that is this one. This is delta V, then this small vector would then be delta V. At this point, you have to use a very important idea, and that is like what I said. You are trying to take the so-called limit of delta t tends to 0. So that means this happened in a very short instant, right? Basically, infinitely small amount of time. So in this case, you can imagine this triangle is basically very, very small, and the angle is also very, very small. In this case, and also we are using a radian for the angle unit, then if you can recall, there was one thing you learned in maths, and that is if you have a segment of a circle with theta as the angle, and this is the arc length, okay, s for example, and this is the radius r, then you have an equation that is s, the arc length, equals to r times the angle theta in radian. And for now, since our angle is very small when the time is basically instant, infinitely small, then you can imagine this s is the same as this distance, okay? I mean, this was a circle segment, and now this is a triangle, but since the angle is so small, then basically they are the same thing. So when you get back to here, then that means if you want to find the magnitude of delta V, then that would equals to V, because magnitude of this equals to the magnitude of V. I can't say V1 or V2 because that is vector, but then if I call it magnitude, then that's fine, times the angle theta. So that's, I will call equation 1. And so again, if you pay attention to the circle itself, this is R and this is R, and similarly, you could also have a arc length, or you can call it the segment here. That should equal to r theta for this one. Okay, so that actually is the amount of the displacement that you move. So that is V times the delta t, which is again the displacement, and that displacement from this triangle is r theta, and that's the equation 2 that you have. Okay, I forgot to put down the absolute value. Okay, so now it should be correct. Alright, so I think the rest of the steps should be very obvious now. What you have to do is you have equation 1 and 2 and you divide them, and then you will get absolute of delta V over absolute V delta t, and then same for the right hand side. Okay, again, the good thing is you can cancel out theta. There's no theta in our equation, right? So it's good to take them out. And then you can rearrange the equation so that it becomes delta V over delta t, and then here we got V absolute square over R. And in fact, this is what we wrote earlier, right? This is acceleration based on the definition. And that's why we can have acceleration equals to V squared over R. Oh, I find out I make a very stupid mistake.
NANI?
Okay, because just now I wanted to explain, okay, so this obviously is a magnitude because this is absolute value. Whenever you put the absolute value, that means you only take out the magnitude of a vector. So the direction, like that information has been, taken away already. So how do we determine the acceleration, then you may ask? Then I was thinking, hey, we can actually look at delta V, because delta V should be the direction of acceleration too. But then now that I realize I make a mistake here, this direction of vector delta V is wrong because this is wrong. Okay. What you should do is, because the vector is v2 minus v1, and that is like v2 plus negative v1, right? So basically, you know, the diagram here. So actually it should be like come from this point all the way to here, and that is actually pointing this direction instead. Okay, I'm sorry about the mistake. And so if you try to put this direction back to the diagram there, and that is pretty much, not pretty much, actually basically it's a direction where it point to the center, alright? I mean, the diagram I didn't draw very well, but then if you can draw it well, then you can find out it's the same direction pointing to the center. So there you have it. Now you have obtained the first equation, A equals to V squared over R. As I said, there are actually more than one ways of deriving this equation, and let me show you very quickly. So this is a summary made by Dr. Tong, a professor from CHK Physics Department, and so I'll put a link in the description below if you want to look at the original source. So the one that we did is actually the top left, this one, subtraction of vector, and this is probably the easiest and require the least mathematics and also imagination. If you want to challenge yourself, I would recommend you to go for try to understand this approach and also the approach on the top right corner here. And these two, if you have studied HL maths and or if you're a HL physics student, you should be able to understand it. So you may want to pause the video now and try to appreciate, read it, and try to understand it. It's actually quite elegant. And lastly, if you still want to challenge yourself even more, try to go for the last one here, all right, called the falling deviation of, you know, the equation itself. So this one requires quite a lot of imagination. So I'm not going to explain it. You can explore it yourself. Okay, and for now, the next thing that I would like you to do before ending this video is, so how do we get the other three equation number 2, 3, 4. I just named it myself, it's not official. 2, 3 or 4 equations down here. Try to think about the definition, try to see how you can get from here to the other three. Pause the video now and I'll show you later. Try yourself first.
2,000 years later.
Because I'm running out of space, so allow me to clear up here, and so you may want to find some other places to write down if you don't have enough space. So the first thing that I would need to do is, in fact, by looking at the definition of the two, here and also here, you should be able to find out a relationship that is, if you divide the two equations, you can get R equals to V over omega, alright? Or if you rearrange it, then you'll be able to get V equals to R omega. So this is actually a equation that you'll be able to use from the definition, and I think this is also in the data booklet. Alright, here it is, right? V equals to omega R. So if you can apply that, so let me write again here, then very easily by the first equation that we proved, V squared over R, then you can substitute that into it, and so you can get V equals to, omega R. So simply omega R squared over R, and so you can get omega squared, R squared over R, then that will be R. So this will be the equation 3 that we have here. Okay, so this is done. And so the next thing that you want to do is you can still recall the definition of omega. Again, omega's definition is 2 pi over t, because it's about how much like time it takes for one circle. So you can get 2 pi over t square, keep the R here, then you would be able to get 4 pi square over t square R, and so that is simply equation 2, right? This whole thing is equation 2. So this is also done. Lastly, you just missed out the equation 4, right? And so you have to recall one more equation that you learned in physics, and that is t equals to 1 over f, because obviously from this equation to the last one, you can see there's a frequency f, right? And so in fact this is very simple. You just have to change the 1 over t. I mean, if you think about it, this is the same as 1 over t equals to f, and so that would become 4 pi square R f square. So this is how you can get equation 4. So here you have it. Now you have learned how to derive the centripetal acceleration formula in the form of v squared over r, and then you can use it to derive the other 3 kinds of format. And so the last thing that I would like you to do, which will be good for you in the long term, and that is go to your data booklet, not this one, not this question booklet, but also the actual data booklet that you have, because as I always tell you, you should keep an actual data booklet throughout the whole journey of IB Physics. Whenever you study each chapter, you're going to put down some reminder for yourself. So here, a reminder for yourself is you should remind yourself that there are 4 centripetal accelerations expressions. So one is here, which is the most fundamental one, and then you can derive the other 2 if you want to. And also here is the 3rd kind without the m. Remember, this is F equals to ma, so the a is omega squared times r. And there's actually the 4th one where you can derive it from this one by using 1 over t equals to f, and then you can get it to be 4 pi square r f squared. So again, these 4 equations will be very useful later on when we approach some examples, and yeah, we'll be using it quite a lot. I hope you enjoy learning physics with me. If you do so, please hit the like button and subscribe to my channel. I'll see you again in the next video. Bye.